for joining us today.
Ana, cuando quieras.
Okay.
Thank you. Shall we start?
Yes. Let me share this.
Yeah, can you see everyone? Can you see the presentation? Okay. To start, as we discussed in our first session, I think it was at the end of October, the 29th or 28th, I don't remember exactly, the analysis of the digital scores are a core aspect in the DIDONE project, and it forms for package number 4. When facing the challenge of analyzing thousands of musical pieces, one needs to design an analytical system that is both consistent and comprehensive, because we are going to to input enormous amounts of data to a computer that would eventually tell us what is going on in the music and to what purpose. This is even more so the case when the pieces span around a century between 1720 and 1820 or the start of the 19th century, with all the aesthetic implication this has, when they are written for varying combinations of instruments and voices and also have lyrics, as is the case of our corpus. Furthermore, we intend not to analyze them from a systematic point of view only, that is, not only thinking of musical grammar, but rather to try and determine whether there is a correlation between the first level musical features or the neutral level and the emotional content that an 18th century librettist aimed at conveying through his texts, that is, Metastasio. For this, the communication between the computer scientist, Paula, and the musicologist, music theorist, me, is critical. And in fact, what we are going to present today is the result of months of back and forth discussions. The first step in the process has been to design the model itself, to determine which parameters we hypothesize may be relevant to our research questions, and how to tabulate and quantify the data so the computer can process them and the calculations can make musical sense. So first, we decided to select a rather reduced number of musical parameters to which many different types of very specific features can be associated. We will look into the list in the following slide. In any case, the idea is that we will automatically extract the data for each parameter independently from the others, developing specific software for each of them. It is important that we follow the same criteria and formats when both extracting and processing the information. Normally, for each parameter, I start by picking a few files and doing all the analysis by hand. Once I'm convinced or almost convinced by the types of data and the way of presenting them for easier understanding, I design the necessary templates with the results of the analysis in them. So Paula can take these templates as models to be produced by the software. Also, I normally write the explanations down so we can always have something stable to work with and to modify. Then Paula writes the code, normally discussing with me the points that were not clear in my explanations or that made no computational sense. And then we check the results obtained with the computer with those I got by hand. That is, we first check the results, we test the software, that the software works with a few areas, perhaps 5, 6, and then optimize the software so it can process large numbers of files in a reasonable time. Also, we want our tools to be applicable to other corpora, no matter the language in which the files were written, I mean, Spanish, English, German, or even the engraving software. We use Finale, but other people may want to use MuseScore or any other software, or the type of repertoire, provided that those files are in XML format. So once our scripts work for us, we start the process of considering other more general features people may find in their corpus. We have approached our list of selected parameters with you can see on the screen by conceived increasing order of complexity. So we establish ground as solid as possible from the beginning. We have already developed scripts to extract and compute data regarding the key, which includes the analysis of modes, the key signatures and their types, the modulations and the tonal relations between them. Also for the scoring, grouping instruments by types and families, and also trying to identify if the presence of a specific instrument is expressively relevant, and also for the tempo and the tempo markings. As some of the computational methods used to extract that data are also taken into account when analyzing melodic construction, we will mention them later in slightly more detail. Today, as you may have read in the abstract for the presentation, we are going to focus on melody. At first, we designed the software to process our vocal parts only, but have then expanded it to be applicable to any instrumental part too. As Paula will explain later when she goes into detail regarding how the melodic analysis software is built, data are first extracted for each file, in our case for each area, and then stored in the form of an Excel spreadsheet in which each row corresponds to a piece, and then each column corresponds to the counts for each feature in the given parameter we are analyzing. The idea is that with all the compute data in the columns, at the end of the project, the data for each parameter will be transferred into a larger file that will contain the data for all the parameters altogether. We will inspect all the data with artificial intelligence techniques so the computer can determine how the pieces can be grouped, attending to their musical features. This has two different paths. First, if we tell the computer the emotions that are expressed in a number of areas on the basis of the CAG theory, as Álvaro and José María explained in a previous seminar, we hope that the computer will be able to determine which of the extract musical features are relevant to each of the emotions, and then give an emotional label to those areas for which we have not determined the passion. Also, in the second place, we can give all the data, the raw data, to the computer and ask it to group the pieces attending to the musical features only. Thus, we will be able to see if the groups that the computer finds are the same or not as those that we determined using an emotional theoretical criterion. This modular system of extracting the data for each parameter first and then merging them has the advantage of being faster than if we built a single software to extract all kinds of data at the same time. However, music is so complex that there are so many stylistics or aesthetic considerations that a computer cannot evaluate by itself. Also, issues of musical grammar may be influencing composers' decisions at other levels. For instance, as Álvaro and I exposed in our presentation in November, the combinations of instruments for which the music was written may have had a direct influence on the key to which the text was set, or the other way around. And in turn, the scoring was definitely influenced not only by the local customs of the theater where the opera was going to be premiered or performed if it was a revival, but also by the instruments available at a certain date. For example, the clarinet cannot feature in our first arias, the arias from the 1720s. Therefore, we also aim at investigating what factors, either musical or extra-musical, may have had an impact on the compositional strategies. And thus, we're also developing software that evaluates trends using very simple averages and deviations, but which are very intuitive for us. And those trends could be observed in specific territories, dates, composers, scoring, keys, etc. And we will do it at potentially infinite levels of filtering, with a consequent increase in computational effort. In this particular regard, you can imagine how crucial our database will be to store the information regarding those extra musical features that cannot be retrieved from the scores themselves. So we will need to merge the information from the database with those that come from the musical scores. For instance, we may want to evaluate the use of specific scale degrees in the melody in the 1750s, but more specifically, not only the 50s, but in the 50s in Milan, when a flute was used in the area, or when the vocal part was written for alto instead of, in comparison with the writing for the most common soprano. In that way, our software creates data reports with the results filtered by the factors you can see on the screen. On top of this, as all the numbers may be too much for a musicologist to process, we accompany the results with specific visualizations. In this way, we find that a compositional characteristic clearly was stylistically or geographically mediated. If we find this, we can minimize its impact when performing the artificial intelligence tasks. For the filtering and the grouping of the pieces, it is important to make it clear that we compute the simple counts in different ways and then try and understand the results. We hypothesize that the most important among different ways would be to first calculate ratios for each feature in each of the pieces first, and then the mean values for all the pieces in the group we are clustering. Instead of summing occurrences and in all the pieces altogether and then calculating the average. In this way, we minimize the impact of the piece length or its textural density, for instance. As an example, if we want to evaluate the weight of subdominant chords in a group of pieces, a piece with 500 bars in comparison to an average of pieces made of 200 bars would produce highly misleading results. Now that the general framework is set, let's move into today's main focus, our software for the analysis of melodic features in music XML files. I will first detail which kinds of data we extract, so we all get an idea of what the program is designed for. And then Paula will go into details regarding how the script is built and also show some screenshots from the resulting reports and the visualizations. For the analysis of the melodic construction of the parts, the voices, we have deemed intervallic construction, range, or ambitus as we tend to call it, and scale configuration as most important. We have split the specific types of data into a number of computational tasks, so the information can be processed in a modular way and also presented in a more user-friendly manner. As most of you have expertise in music, I won't explain what an interval is or what their types are. But please, if you have any doubts, just send a message in the chat and either Paula or me or any of our colleagues will reply. In the first place, we retrieve data regarding the average number of semitones per interval in each piece or group of pieces if we are speaking of the grouping phase, what we call intervallic ratio. We calculated this regarding the direction of the interval, yes, its magnitude. This is something we have already explored in a couple of papers that we have presented in conferences in Czeski-Krumlov and Berlin when we made analysis by hand. In general, we have found that natural male voices tend to sing with larger intervals. So female characters in whose melodic parts the interval ratio is higher or larger than the average may indicate that the composer is trying to convey some sort of supposedly masculine attribute for that character. That is the case of the character of Didone in Didone Abbandonata, whose aria Son Regina e Son Amante, in average, shows an intervallic ratio markedly larger than her other arias in the libretto, taking all the versions into account and then making the average. Interestingly, the text for this area, and Alvaro will explain this when in the seminar devoted to Didone, in this area, Didone epitomizes traits such as autonomy, independence, and power or rule, which at least traditionally or in the 18th century have been considered more typical of men. We also compute differences and other kinds of ratios, but we won't go into details. In a parallel way, we compute the syllabic ratio, or the average number of notes per syllable in the case of vocal parts in parts where there are lyrics. Perhaps, and this is just an hypothesis, composers would set a more agitated passion to a faster declamatory style, and conversely, in a more restrained emotion, a character would be granted more time to dwell in fiorituras, or the other way around, we don't know yet. We also think that the ambitus can be relevant, and not only the average or the mean ambitus, but also the specific streams, to understand its meaning within the maximum part range that the static ambitus is occupying, I mean in the whole range where the specific ambitus is located. We offer both the ambitus interval, how large the ambitus is, and also the names of the notes at its extremes. As I presented in a paper in the AMS conference last November, the part of the tessitura for the various voice types was differently exploited depending on where the opera was being premiered, no matter who the composer was. In the case of composers writing different versions for different theaters around Europe, we can find different uses depending on where the opera was going to be premiered. Specifically, male voices in Spain and Portugal seem to have tended to be used in a lower ambitus than in continental Europe, even in the case of the same composer. I'm thinking of Jomeli, who has different versions of the Mofonte. One was premiered in Lisbon. This is the case, the use of the voices, and also when they wrote for the same singer in different parts of Europe, in Europe with perhaps 1 or 2 years of difference in time, the use of the voice is very different. And we think that perhaps it seems that in the peninsula, they tended to write for male voices in a lower register, trying to emphasize the supposedly masculine attributes. And in the same way, they tend to use feminine voices in a higher range. To finish this section, we also think that for our purposes, and in particular when applied to the vocal parts, the marked presence or lack of specific intervallic lips, as well as their absolute magnitude, can be telling. Preliminary explanation suggests that they might be related to the expression of specific emotions, and also to technical demands made on instrumentalists if we apply this kind of analysis to instrumental parts. This is in relation to what I just commented regarding Didone's Son Regina e Son Amante aria, where in fact the larger intervallic ratio is produced by a striking number of perfect eighths that are normally associated to male voices. We compute the presence of specific intervals in our group of pieces, taking into account both their direction and possible enharmonic presentations. That is, we care not only about the size of the interval as measured in number of semitones, but also about its music theoretical qualities. That is to say, a diminished 4 and a major third have the same number of semitones, yet their melodic and expressive value is completely different. Especially in the Mofonte, we have noticed there is one aria, Misero Pargoletto, from the 3rd act, with a significantly greater use of augmented fourths and also diminished fifths. Indeed, the difference with respect to the average ratio is striking. We think it cannot be a coincidence that it is precisely this aria where Timante, the first male lover in the plot, expresses his horror at having committed incest. And also Alvaro and I will discuss some other specificities of the general trends found in all the versions from this area in a future seminar in the upcoming months. As there may be dozens of interval types in a given corpus, we think that grouping them by types, I mean perfect, minor, major, augmented, diminished, and so forth, by magnitudes, step motion versus leaps and repeated notes, and within those, the direction, ascending and descending, could serve an important analytical purpose too. This is the reason why we include this third aspect in our reports. Trying to understand other reasons behind composers' decisions on melodic construction, we also want to evaluate if the emphasis on specific melodic degrees was relevant to the expression of such emotions. And for that, we compute the presence of melodic scale degrees in our paths in respect of both the global key of the piece, the key in which the piece starts, and also in respect of the local key through the various modulations that may happen. We also take into account the differences in leveling between the major and the minor mode. That is, for instance, an A flat in C major would be labeled as B6, but in C minor, it would be a 6, just a simple 6. That's why, again, we perform calculations at the area level first. The hypothesis that prompted the analysis of this feature is that the different regions or even specific degrees in a melody may show a correlation to the emotional content of the music. For instance, and this is an hypothesis as well, a melody with a more marked presence of the first degree in the melody may correlate with stronger, more assertive emotions than, for instance, a melody circulating more around the fourth degree of the scale. And that includes the leading note of that fourth degree, as we will see reflected in the corresponding visualizations. Finally, and this may be relevant to both vocal and instrumental repertoires, although with dissimilar implications, of course, we compute the presence of the various clefs in the parts we select for the analysis. In our case, this indicates the type of voice for which the arias were written, soprano versus alto, for instance. But in the case of instrumental music, it could give clear hints on the tessitura range in which the instruments are employed. Now that we have an idea of what kind of features we extract and compute the data for, Paula is going to explain the computational methods employed and some artificial intelligence techniques we have started to apply. We will also show some of the visualizations that can be automatically obtained with the software. But before that, I want to stress that we will be sharing results for a corpus, a test corpus made of 138 arias. Yes, that as I have been showing with some of the case studies, we hypothesize that general average won't be very meaningful for our purposes. What we think will be meaningful instead would be to observe specific tendencies in the particular groups of or subgroup of pieces. And that's why we are making the data filtering. So musicologists can try and find a musically meaningful relation between the numbers obtained on the one hand and the music and the text on the other. In particular, the groupings by aria title and passion, which we are also performing, will be most telling when trying to determine whether a specific melodic feature among those I have been explaining may enter into play when it comes to expressing the emotions contained in Metastasio's poetry.
Okay, I think it's my turn. Thank you very much, Anna. Now that we have explained what features our software computes, let's present the workflow. Okay, it's composed of two main modules, the information extraction, or the reading process, as we also call it, and grouping and visualization, or the writing process. The whole system is written in Python, and the data are extracted from the digital scores in music XML format, thanks to the library Music21, although we will cover that afterwards. Okay, so to get started, the first module loads the information from both the XML chosen by the user and a JSON file where the user can annotate the specific information about the corpus, such as the year of each piece, composers' names, etc. All this information will be used afterwards to create the grouping of pieces, for instance, to group all the areas by year. This writing module generates a set of intermediate raw files without any style, just the data, which serves as communication with the second module, which is the writing process. In it, information grouping is performed and it generates Excel reports and visualization, as it can be seen in the graph. And they are carried out thanks to Matplotlib's library. Okay, so we will see first the first module on information extraction. In the left-hand side of the slide, you can see a snippet of a music XML file representing two notes, C and D. You can see the starting label of the note and the closing label. Again, for the second note, again, the starting label and closing label. They are both squared in red. And inside, you can see several attributes, such as the pitch, the voice to which it belongs, the type, the lyrics, if it has. Okay, so when loading this file to Python using Music21, a list of parts is generated, which in turn contains a list of bars or measures with a list of notes and rest within. Okay, so the list of notes belonging to that specific measure is shown in the center of the slide. You can see it. It has three elements, a rest, a C, and a D note. Okay, so if we expand, for instance, this last note, we can see a big amount of information. Okay, so you have it here. As you can see, Music21 returns a big amount of information for each note, but I will focus on the most relevant for our purposes today. We can find some Boolean values indicating if this object is a chord, a note, or a rest. A Boolean value in computer science is a data type that can only indicate true or false. So you can see that it's not a chord, but it is a note and it's not a rest. Okay, so to continue, we find information about if this note is linked in a tie, which it is, if it contains lyrics, and in case it is, the text attached to that note. You can see it here, it contains the lyric per. Finally, well, we can find also the measure where this note is located and the simplified note name without the octave. Okay, so I would like to highlight that we have had the opportunity to contribute in the development of Music21 by helping the MIT to improve the lyrics processing, as when doing this exploratory analysis, we found out that there was an issue with some lyrics. So actually, if you check on the collaborators tab in the Music21's GitHub, you will see the DIDONE project there. Okay, so thanks to Python, we can extract the list of notes in the score previously loaded. And from that list of notes that you can see at the left-hand side of this slide, we can compute the list of intervals between those notes, which in the example in the middle of the screen are shown in form of a tuple, containing first the number of intervals present between, like the number of semitones, sorry, present between those notes, and then the interval names. Okay, another thing that we can also do is to extract the list of lyrics present in each note. Okay, so regarding the second module, grouping and visualization, we present this example of an intermediate file, okay, which, as I said before, it is used as a bridge between both processes. It is composed of general information that you can see first, and then information regarding each feature, which in this case, this is what would be released in the case of the intervals. As you can see, each interval has a number attached to it for each score, the scores being represented in the rows. In other words, we can see how many times a given interval appears in each score. Okay, to illustrate how we perform the groupings, we show this example in which the data are grouped by key. In this case, as we're talking about interval frequencies, the operation that we have to apply is a sum. That is, for each key, we sum the values regarding to each interval. Okay, you can see here that we have the key relating to each area or each score, and we are grouping by key. So first, we have highlighted the ones that have key C. Okay, so we have 2, and we have performed the addition of all the interval frequencies. So we have this resulting table. Okay. Here is a GIF of the program execution. As you can see, the program is built to be executed in the terminal, and it can be really fast, but the first thing that the user has to do is to input the voice that he or she wants to work with. In this case, we have chosen the vocal part, which is part number 15 from the list of parts present in the corpus. Okay, you can see all of them here listed, and we have chosen the number 15. Okay, then a progress bar is shown representing the state of the reading process. Then the same thing is performed for every single grouping factor in the writing process, those that the user can fill in the JSON file. We can also obtain the result for potentially infinite levels of grouping or filtering, although the computational time increases very significantly. Okay, so when finished this execution, we will have the folders and files in our computer as shown in this next slide. Okay, so these are the 7 Excel files generating along with the visualization folder, which contains all the graphs and data representations. At this point, let's start having a look at each of the reports. We will like to highlight, although Anna has already done it, but the following examples are the result of the execution of the program with 138 music XMLs. That is, in our case, 138 areas. And we have done it using 1 level of grouping. Okay, regarding the values report, we have this snippet, in which our areas have been analyzed in groups by key. In it, we can see that the most frequent key is D major. Okay, you can see it here, as it has been observed in 24 scores. We can also observe that the mean intervallic ratio is 2.6. You can see it here, meaning that 2.6 is the mean number of semitones present per interval in the 138 scores. The absolute intervallic ratio here, as it takes into account the direction of the interval, that is, if a minor third is descending, it will take value -3. It returns approximately 0. So we can conclude that the ascending and descending intervals are really balanced. Finally, we want to highlight the syllabic ratio found here, as it represents the number of notes per syllable. It is in the group of B minor pieces, okay, found here, where there are fewer notes per syllables, 1.342, while the scores in B flat major, here in this row, are the group where there are more notes per syllable. Okay, this slide shows another sheet of the same Excel report, in which information about the ámbitos is shown. That is, it summarizes which the lowest and highest notes are in each group, along with their MIDI indexes, as well as the mean lowest and highest note. Regarding the ámbitos, you can see that the largest, smallest, absolute, and mean ranges are shown for each group, along with the number of semitones that they represent. This visualization, also generated automatically, shows in box plots the most frequent values for the lowest and highest notes, as well as for the ambitus. These circles, okay, that you can see, represent outlier values. This is to say values that are considered valid in our case, despite being very uncommon. Okay, so regarding the intervals, this report shows each interval represented in the corpus and their frequencies grouped by any single factor. As this report is straightforward, we will only stop at the visualization that summarizes it. So this visualization shows a bar plot of the most frequent intervals over the 100%. The graph also indicates the interval's direction, that is, if they are ascending or descending. Nevertheless, in this slide is shown the intervals absolute, and that means that we are showing them without their directions. And as before, it is represented over the total. Okay, so this next report shows the values horizontally, but what does horizontally mean? It means that results are represented over the total of the group. Remember that in the reports we have shown so far, pieces or their groupings occupy rows and musical features the columns. In this case, pieces are grouped by time signature. Clearly, the most frequent time signature is 4x4, as it has been used in 71 of our scores, which are more than a half of the corpus. Okay, you can see it here, but let's focus on that group. We can see that 13% of the notes of the scores in this group were the same note as the previous one. Also, 31% of them have an interval lip of 3 semitones or larger, and more than 55% of the intervals have 1 or 2 semitones, indicating the frequency of step motion in the vocal part, which is the one that we selected in the first step when running the program. Okay, so this visualization is generated along with the report to help to understand the information more easily. The pie charts show the percentage of ascending and descending intervals for each interval type: stepwise motion, leaps, but also perfect, major, minor, augmented, and diminished. Okay, so regarding the emphasized scale degrees, we generate these graphs, but to explain this, I will give the floor to Anna as she designed this representation.
Thank you, Paula. This graph with the circles represents the weight or presence of the specific melodic degrees in the 138 pieces selected for today's analysis. The circles are disposed in the two-dimensional space in a way that tonal relationships and tensions are reflected. You can see that all the melodic degrees forming the tonic chord, that is 1, 3, and 5, appear on the right-hand side of the graphs. Degrees in the subdominant region, 2, 4, and 6, appear on the on the left, whereas those forming the dominant chord, 2, 5, and 7, appear at the bottom. Also, the colors represent the mixing between the degrees and if they can belong to different regions. The leading note, degree number 7 or /7, if we are speaking of pieces in the minor mode, it is not at the same horizontal level as 2 and 5 because it is tonally attracted towards the first degree, and thus it appears at its bottom left. The same happens with all secondary leading notes and other less represented degrees that are tonally attracted to the diatonic degrees in the scale. As you can imagine, the size of the circles directly correlates to the presence of that degree in the piece or pieces analyzed. This graph represents the weight of those melodic degrees in respect of the global or the main key of the piece. But the following one, the one you can see here, shows the results in respect of the various local keys to which the music modulates. If we pass the slides back and forth, we can see that the ratio of the first and the fifth degrees especially change quite significantly. This is because almost all areas modulate to the dominant halfway the A section. And therefore, what in respect of the main key of the piece would be a 5, in respect of the new key, the one after the modulation, would be a 1. Also, degrees that seem very far in the tonal space in regards of the main key now disappear when we make sense out of them in the perceived tonal context, in the real context in which they appear.
Okay, thank you very much, Anna. And I will continue with the machine learning experiments that we have carried out, because as I explained before, the data extracted so far can also be used for machine learning purposes. Thus, we carried out a brief experiment to cluster our data and see how artificial intelligence groups them. As we started working with 53 different attributes in our ARIA files, we had to perform a feature selection process. To start, we studied the correlation of the variables, which you can see in this correlation matrix. The darker the color, the stronger the correlation between those variables. Nevertheless, there were still many different variables highly correlated. So we decided to perform an algorithm called principal component analysis. This algorithm reduces all the attributes to a given number of them. In our case, we decided to reduce these 53 variables to a 3-dimensional space. In this manner, we were able to perform different algorithms such as k-means, the result of which can be seen in this slide. This algorithm groups all the areas in several clusters identified by a color. The numbers aside in the color dots are the unique IDs for each area. This is something we will explain in future seminars. We can see that each type of areas is assigned to a certain space in the graph. The purple ones are the ones with a higher C3 value. You can see the variable C3, and they have a higher level, while the orange ones have a higher C1. Okay. Of course, this is an approach in which the areas are grouped in clusters based on their similarities, although these groups' names are 0, 1, 2, 3, and 4, as you can see in the legend. In the future, we expect these groups to be anger, sadness, happiness, and a few other emotions. In line with the project's main objective, we aim to apply these algorithms to emotion analysis. But we also applied different algorithms to the same data set. For instance, this is called hierarchical algorithm. And it allows us to explore the dendrogram. It's generated to group the areas. The closer the areas merge, the more similar they are. We can see in the light blue section that areas number 92 and 61 are really similar, while others are grouped at a higher level only. Okay, so this is it. Thank you very much for joining us and attending this seminar. And thank you to all the members of DIDONE. Without their work, neither Anna nor I could have reached this point. Thank you very much.